All right, everyone, let's get started. Okay, so yeah, today is 365, so machine learning foundations. So let me share screen. Okay, so as you know, we are in the third phase of the class. First phase being, like distance metric based systems, right, that we looked at as part of the algorithm. Then we did probabilistic methods, right? Specifically, that's the main theme, although there's a lot of overlap between a lot of these, right? So there's a lot of overlap. And then this third phase, of course, is the most important one, I would say, at least today. Could be that 10 years from now, they come up with a probabilistic method, and that's just revolutionary, right? So I don't know. Nobody knows really. But this is where we are right now. So we have to be adaptable in all of this. So as you can see here, you should be seeing the machine learning foundations on GitHub, and we are basically on neural nets. And these are all the algorithms that we're going to cover. Finishing up with TensorFlow, which has its own little folder. All right, so last Tuesday, I went over the history and context of machine learning or neural networks in general. And I said that the starting point is something called the perceptron. So that's where we are today. So we started the perceptron on Thursday, and then I'm going to wrap it up today. Now, all of these have very similar elements, okay? So it's almost like this is, like the grandfather and the father and children. So there's, very strong similarities. One builds on top of the other. So as I said, just because we're looking at the perceptron right now, and that's not deep learning, that doesn't mean that it's not important. It's actually very fundamental, because what's important about this is that deep learning will be more complicated, but you're looking at older versions. And so it's easier. So imagine a car engine today, right? Versus a car engine from the 1970s. So it made more sense to you what everything was for a car in the 1970s, whereas now, right? Still some of the elements are there, but not all of it. Does that make sense? So it's really important that you you pay a lot of attention, in particular because perceptron and linear regression are also very intuitive. Okay, so there's also that element that they're very intuitive, and so they're easy to understand almost, right? That's the trick, and that's why if you think about it, when you would learn about machine learning, when you would learn about neural nets, in the past, people would just jump at multi-layer perceptron. This is how it was taught to me. So imagine how stressed you were, and it was almost this thing where you were disconnected. You thought linear regression and multi-layer perceptron were these two totally different things, when they're not, right? They're almost like literally the same. One adds more to the original. All right, so that's really important to keep in mind, okay? So hopefully I'll go over understanding how you train linear regression is key to understanding everything else, okay? So I'll go over this. I'm hoping that this was taught to you in the statistics class, and it probably was, and then I'll just stress it and make this point. Because I remember I was in a statistics class many years ago when I had that aha moment, and I finally got this, all right? And if you get this element, it'll make sense, okay? So that's really important to understand the whole mechanism. All right, so today we're gonna look at, finish up the perceptron. So I need to go into Jupyter Notebooks, I believe. Okay, we're going to go to the course. Should be Perceptron 2022. So this is the one that we were working on last Thursday. So we should wrap it up, and then you should have some working code for this. So I need to share it. All right, so if you guys are on Zoom, you should be seeing this code here. All right, so we're gonna go over, you know, just the perceptron where we were. I just kind of quick recap, but I remember we pretty much did everything except for the fit function, so the training. Okay, that's what we're gonna do. Now, keep in mind in all of these elements, at least in the perceptron and in the linear regression, we're trying to fit this equation down here. Remember, we already went into the intuition that we have some inputs. We need to know the importance of each input, right? And that's called the weights, right? But those weights are not known initially. So we need to figure those out. And we could, of course, if we had a quantum computer, we could just randomly think of every possible weight in the world, try all of them at once, right? In theory, right? And then just get the answer. And it would be like that, but we don't have that technology. So we have to find, we can't pick everything at random. That's impossible, and try it, you know, that wouldn't work. So we're not at the quantum computer, and what we have random doesn't work. So we have to find something in between, and that's where the algorithms come in, like stochastic, something called stochastic gradient descent, which is an algorithm that we'll talk about and throughout these 3 lectures of perceptron, linear regression, and logistic regression, right? So they're key to understanding how you train the models. And it's surprising because it's a simple method. There's only one, right? There's only one way of doing this with these algorithms, and it works. That's the amazing thing, right? That it actually does work. All right, so we were at the perceptron. So here we have the libraries, right? Then we had the accuracy metric. We had already talked about this last week, so I'm not going to repeat. The activation function, remember, I told you that this is a function called a stepper function, the way that we have it, right? So I even drew the little step function, right? So if you remember, you can go back to that video and see the step function. And so basically it means any value x greater than 0 will be 1. Any negative value, so that is less than 0, will be 0. All right, so it's basically a step function like that, 0, 1, right? So that's basically the idea. The predict function is the dot product function, so we went over this. So remember, you just multiply x times the weights plus bias. Here's the equation. Just remember, this word dot comes from the fact that we're doing a dot product. So instead of multiplying 2 variables, we're multiplying 2 vectors. But because we want to be even more efficient, we don't just want to give one sample at a time, right? So we give several samples at a time, so that becomes a matrix, and that works as well, right? So if we multiply a vector times a vector, it gives us a value. If we multiply a matrix times a vector, it gives us a vector of values for each one. So we need, it's because for loops are not efficient, so we have to do those operations more efficiently. All right, so that's the predict function. So we do the dot product, that gives us the linear output, and then we run it through some activation function, which basically converts any value minus infinity to plus infinity into either a 0 or 1, right? That's the mapping, that's the activation function. We created some fake data, make blobs, so 150 samples. It's got 2 features basically, okay? So X1 and X2, and we have centers and cluster standard deviation and a random state. And all of this to initialize our data that we can use. And then we perform a train test split on X and Y, and that's just so that we can have a data set for training and then a data set for testing, basically. Then after that, we have our 2 functions, fit and predict, right? So predict, we already described. It takes, so this is actually very important, very key. This didn't used to be the way that you thought about machine learning. You know, at the end of the day, machine learning is architecture, right? A neural net, and then training it to obtain the weights. And then the weights are a thing of value, especially nowadays when you're training on incredibly large data sets, right? Remember what I said. So you're not Google, but Google will have a lot of data, and they now everyone shares their weights, their models. So we live in a new era where we have pre-trained models for a lot of tasks, right? And then we can just specialize it to our own particular one. So that's really kind of the future, and that makes you more powerful. That makes all of you able to solve problems that 5 years ago only Google and the other ones, Facebook could solve. Okay, so it's pretty interesting. So even the way that this is written, we actually do the fit, and that gives us the parameter. These are called the parameters usually, actually. And PyTorch, for instance, which is another language, you basically treat these separately. It's a separate entity, like an object. So it's usually called the parameters, and it's made up usually of weights and bias. And then notice that we pass the weights and the bias from our train model into the predict function. We also have the X test, and this will give us the Y press. And then we just calculate accuracy. So for this code to work now, all we have to do is finish up the fit function. All right, so this is where we are in wrapping this one up. So let me just see you guys from the class. All right, so that was kind of a review. So now let's go over the fit function. This is an important one. I'm going to go over it. It's not really that long. And as I said, what's really important about this is, at least for this class, for the end of the semester, we're always pretty much going to follow this template. You can think of it as a template. When I do deep learning, I like to have templates, right? So I'm very big on that. So because code can get complicated, right? But you have your template of functions, and you just know, okay, I need this function, but it has to change, right? So one example is the activation function. It probably needs to be another one. Or the fit function. You know, it's like this, but different, okay? So keep that in mind. But overall, at least for this course, until the end of the semester, we'll be doing, the same template basically. So let's go ahead now and just finish it up. And then once we finish this code, we'll run it, and then we'll be able to start the linear regression task. Okay. So this is, we're fitting for a 2-class problem. So we're gonna do here, let's just say for 2 classes. Now the 2 classes are, remember, 0 and 1. Okay, that's really shown here, right, in the activation function, for instance. So first of all, fit, we can see it takes X train and Y train, right? So it takes these 2 parameters. So I'm just going to go ahead and copy them. Fit takes X train and Y train. All right. So we've got X train and Y train here. Those are the inputs. Now I'm just going to go over, do one pass first. Let's see. I'm just using my own GitHub. Let's see. So what do we need? We need we need several things. What does fit return? Let's start there, right? What does fit return? It returns the weights and the biases, correct? So those are the things that we have to calculate. So let's initialize that. Let's start there. So weights. And what does weights look like? Well, weights is, we have vectors of what size? Of size 2, right? So the vectors have 2 samples, x1, x2. So I switch over here. Let's switch to the whiteboard. This is important because this is architecture. So we have to think a little bit about it. So we have everything for our example is a vector like this. This is input. Notice that now I'm starting to write very much a lot in a neural net way, right? So I'm writing like neural networks are done. So this is x1, x2, right? So the example here would be, although this data is random, right? You know, we could say that each sample, sample 1, sample 2. So this is, let's say, cars. So then this is, you know, year 2008, and then horsepower, I don't know, 265 horsepower, something like that, right? You guys see that? So these are the values. And then another sample is a 2020, and I don't know, that's 365 horsepower. You guys see that? So this is what the data looks like here, okay? So now what we need to do is we want to predict, you know, an output, right? A value. And so we only have one neuron on the output here. And so we really need the weights here, right? So that's going to be W1, W2. You guys see that? And so this can be treated really, if you look at it, is X1, X2, W1, W1, W2. Do you guys see that? So really, this is usually referred to as the weights matrix. You see that? Weights matrix. And it has a dimensionality of number of features, n features, okay? And actually, sorry, I did this wrong. This should only be like that. Weights. Right, so this is going to be W1, W2. There's only 2 weights. If I had left it the way I had it, I was wrong, right? Because we would have had 4 weights. And there's no 4 weights. So there's only 2. So really, this W, what's important here is that this actually represents the next layer. So in this case, hidden 1, which is actually output. But this later on, as we start talking about neural nets, hidden layers will come into play, right? At least first hidden layer. Okay. So this is a weights matrix. Basically, this is a tensor also. And really, it's a vector because it only has, if we just look at this, it only has 2 values. Does that make sense? This is important, actually. This is one important aspect of this. Are there any questions about this idea? All right, doesn't sound like it. Given that we know the dimension, so I just showed you, right? So now I'm going to ask you a question. Let's see if you answer it. I need to initialize a vector for the weights, right? What can I use for that? In the past, we have used the Numpy zeros, right? Now, remember what I said initially, actually, you probably don't want to initialize these weights to zeros. And in fact, when you do neural nets that are pretty complex, you don't. Instead, what you do is you initialize the values randomly. But randomly sometimes from values from some distribution. So usually the world follows a normal distribution, right? So even particle physics, right? So if you guys think about a particle, supposedly a particle, you cannot predict where a particle is going to be, right? That's the whole idea in physics. That's true for one. But as you start doing thousands of them, what's going to happen? Those particles exist in our world, and they'll start to have what? What is the name of that shape? The bell shape, the bell curve, right? Normal distribution, which basically means a mean and a standard deviation. So a lot of things follow that. So really here, a better approach would be to initialize this to not zeros, but some distribution, normal distribution of random values. Okay, but just to keep it simple here, we're not. So then I need to initialize this to a vector of zeros, right? How many values are in this vector? 2. Very good, right? So, and this is going to be W1 and W2. So that means then this value should be 2 as well, right? So we could just hard code it as 2. But what if our neural net later changes to 3 values or 4 values, right? We want it to be generic, right? And so instead of hard coding numbers, which is always a really bad idea, right? You should always put in parameters, basically. All right, so I'm going to do then that I'm going to say that this is going to be size of n features, because remember the features are x1 and x2, right? And so now I need to get n features from something, right? So n feature is what is in the x train, right? So I just need to get x train right, so from x train dot shape, okay? We're gonna get the values. So actually this will return x and y, right? So then let's say n features is the number of, no, sorry, actually this will be n samples is the first one. All right, so n samples will be the first one. So x will have however many, I think there's like 120. And then n features will be the number of columns, basically, right? So we have n features as 2. And now we have our value here for this. So we initialize it to 2. Another thing that we're going to need is something called a learning rate. Learning rate. So usually this is a value that is somewhere between 0.01 and 0.0001. What does that mean? It means that we're going to, in the fit process, we're going to look at samples one at a time, right? We're going to look at them one at a time. And then we're going to make some adjustment to our weights, right? But there's a question of how big an adjustment should we make to the weights? You know what I mean? Like if I'm going to change the weights every iteration, I'm going to add a value to them or subtract a value from them. Should that be a really big value or a small value? What do you, small, right? But how small? Infinitely small? Yeah, go ahead.
It should be small enough that you can still tell a difference, between the different weights, but not too small that you can't tell. Measurably small.
Measurably small. The problem with too small is that it would take too long. So it's this scenario. If I do this, and I'm going to you, it's gonna take 10 minutes, right? So that's a bit. But if I just jump at you, that may not be a good thing. Right. Scare you, right? And that's basically the analogy here. You know, you have to find a right pace where it doesn't take forever, right? Or it's not too fast that you miss things. Okay, and that's what we're going to think about. So the learning rate is really important. I'll give you a nice analogy later on. I'll just say it right now, of a giant walking on mountains. That's the best analogy for what optimization does. Okay, because remember, everything that we do is equations, right? And equations, just like the line equation, circle equation, can be plotted. So there's shapes in a plot. Do you see that? And they're actually like mountain ranges, you know, with peaks and valleys, right? If you think of it that way. And so we'll see later on that the best analogy for optimization is a giant walking on those mountains. So what's the idea with a giant walking on those mountains? If they're a giant and if they take a big step, they'll just walk on the peaks, never looking into the valleys. The treasure is in the valleys, if you want to remember. Those are easy analogies that you can remember to understand what's going on in the math of optimization with calculus and everything, right? What's the, you know, you've probably heard this, like in calculus, right? There's derivatives and the integrals, right? And the integral allows you to find have you heard of this, the area under the curve? You probably saw that, right? So the area under the curve, it means, there's a shape and then there's from one point to the other, the area, right? So calculus comes in a little bit into this, although we don't need it. That's why we have TensorFlow, and certainly we don't need it for the Perceptron, but just be aware of that. The optimization goes into that realm because everything is governed by equations. Equations can be plotted. And so we have these functions like the sine, cosine, it's whatever, all these are just shapes, right? And so we search on these lines, if you will, for things. So that'll become a little bit more obvious later. But for now, the learning rate, as I said, the best analogy is that the update that we're making, how big or how small, okay? So for now, we're just going to say 0.01. I always encourage you to play with these learning rates. Make it bigger, make it smaller, and see what happens. A bad learning rate will derail the entire model. That's for sure. All right, so we have the learning rate done, and then we have the shape. So now if we think about it, remember that our equation here will look like y equals w1 times x1 plus w2 times x2 plus ... and then the bias. All right, so just don't forget, that's really the equation we are trying to create. Okay, so we've defined those parameters. Now the bias, of course, also needs to initialize. So that's just for our example, for our purpose, is just that. Remember, the bias is just with the line, right? So where we have the slope, but we figure out where we start in the y-axis. All right, so intuitively, we have that parameter and we have it here in machine learning as well. All right, so now that we have this, we need to take the labels from Y-train, right? That we have the labels. Currently, these labels are just, because of the way we initialize this, they're just values, right? Any real valued numbers. Do you agree? So we need to change these Y's into labels of just 0 and 1. So the criteria for this is pretty simple. As we said, if the value is less than 0, it's a 0. If it's greater than 0, it's a 1. So that's just, I'm going to create then a new variable here. Just going to say y underscore, and it's going to be a numpy array. So it's going to be a numpy array. And then in here, I'm going to do a list comprehension. So the list comprehension will be for I in Y train, right? For Y in Y train. And so I'm just going to say one if I greater than 0. Else 0. See, that's the same thing. So we're just going to turn all the values into either 0 or 1. So it's basically that stepper function. Okay. So that, it's a little bit of just getting things set up. We can always print the Y's just to make sure. So you can do Y underscore. Right, and now we are ready to do the training, right? So the basic training means that we have to look at every test sample, look at it, and do an adjustment, right? So that involves some kind of an iteration. Now, this part is always a little bit tricky to understand. Took me a long time, actually, to get this, to get the why of this. But this is called, I'm going to say n epochs. And I'm going to set it to 1,000. So in machine learning, it may not seem like a problem to you, but to me, I used to think that you would only show all the data to the model once, and that's it. And I thought for some strange reason that if you showed the model the same data set more than once, that was cheating. I don't know why. So that may not be for you a problem, but at the end of the day, it has been proven that it's a very good recommendation to show the same, all the data set to the model more than once. And in fact, many times. So what you usually do is that, now what is recommended is that you take the data set and every time that you're about to show that whole model or that whole data set to the model, that you randomize the samples. They're still the same one, just shuffle them around, right? So that you're not always showing the same pattern. But it is recommended to do that. And so this is the term of the number of times that you show all the data to the model is called the n epochs, or the number of epochs. So you can see here, I've selected 1,000. And so basically we're going to create a for loop that is for this underscore here. So for in, let me just finish it. So for in range n epochs. Okay, so that underscore just means I could have done for element in range n epochs, and then I would have had the value in that variable. When you use the underscore, it just means that you want to do the for loop, but you don't care about the variable. You're not going to use it. So just means repeat the whole for loop, but I'm not using any variables. Do you guys see that? All right, so so that's the idea. So in this case, this for nothing in range n epochs means I'm going to show all the data to the model n epochs. Okay, and that is that's the first for loop that handles showing it all the data. Then, of course, we need one for loop that shows it the data, right? So there's two for loops that we're going to do. So in this case, I'm going to use the enumerate function, which allows me to iterate through, a set of values, but it gives me the ID and the value itself, right? So when I use the enumerate function, so I'm going to say for idx comma xi in enumerate x train. Okay, so now I'm in X train. X train is 120 by 2, so don't forget that. We're going to grab all the samples here and the index so that we know that this is index 3 and this is sample X1, X2, right? So all the two features. So now that we have this, we are ready then to do the actual training. So to do the training, what do we do? So to do the training, I'm going to switch over to the whiteboard again. Go to another page. To do the training, what we need to do is we're doing a for loop, right? Now, our goal is, given some data, X1, X2, right? And some values here and some values here, and these are samples. We have the labels already. We have Y. 1, 1, 1, 0, 0, 1, 0, 1, right? Those are the labels. Our goal is to predict a value. So let's call it Y hat. Okay, it's another Y. It's the Y predicted. I usually call in the code these Y true and Y pred, right? That's a very common convention. We'll probably use that convention all the way to the end of the semester. So what's going to happen is, ultimately, if this happened, if we use our model and this happened, what does that mean? Yeah. The weights are correct, exactly. So do you need to train the model anymore? According to this, no, right? Because it's perfect. But obviously, our weights are not correct, so we're not going to get that, right? We're going to get a lot of errors, right? And so what's going to happen is every iteration, whether we give it just one sample or a batch of samples, several samples, it's going to predict some values. Let's say we're doing 3 at a time. So it does this. out of those three, only one was a correct prediction. Do you see that? So now what we need to do is, but this is all we know. So I'm trying to show you that the algorithm, which we have here, right, our model, this is our model, right, has some bad weights, W1, W2, and we fed it some input, this one. It predicted some output, 0, right? It predicted an output, 0 here. But when we compare that to the real value, so this is pred, this is real, they're not a match. Do you see that? And so now we need to go and say, we need to do something. We need to look at 0 and 1 somehow, right? And say, okay, well, based on this, I need to go back and adjust the weights, change them a little, and then I'm going to do it again. But not with this value, with another one. So I'm going to go in and grab the next one, feed it into the model, right? Go through the model, get another value here for pred, for another sample, and maybe that one's correct. So if that's correct, then again, we analyze it, we go back to the weights, and maybe the adjustment now, because because they were correct, is very tiny. That is, we think, okay, those weights were good, right? So don't change them that much. So we change them very little. Then we repeat it again, S3, run S3 to the model. It gives us now 0. Let's say this one changed to 0, and then now this one is 1. It's not a match, so we analyze it again, go to the weights. What do? Small change, big change. Small but bigger than when it's correct, right? So a little bit, or maybe just for the weight, for the specific weight, actually, we adjust it. But we adjust the weights again. And so do you see this cycle? So this is a cycle that's happening kind of like this, right? Do you see that? So we're always predicting. We start predicting even when our weights are terrible. In our case, our weights are, they're very bad. They're 0, right? Initially, but we're going to start. That's where the bias is helpful, because the bias is going to change a little bit as well. Do you see that? And so we're repeating this process. Eventually, the weight should be good. All right, at least that's the hope. Got it? So the first thing we need to do is we need to predict, right? We need to predict even though our weights are bad, but actually we can do that. Any model, once you've built the architecture and initialize all the parameters, will predict. It'll just predict badly. Whether it's a perceptron or the best deep neural network you can create, it will predict. It's got bad weights. Okay, the parameters, which nowadays can be billions of parameters, right? So a lot. Anyway, so we're here. So the first thing we're going to do then is predict. So because we're using vectors, what is the function for predicting? Y equals W times X plus B. See that? And so this is the equation that we are using or predicting on. So now I'm going to create it. Remember, this is still linear. It's a linear function. Remember, what that means is we're creating straight lines. The line equation, right? But the activation function is the thing that makes our linear nonlinear. But for now, let's just say linear output. This variable usually is called output or Y pred, it depends. It's any name, but those are the usual notation. Once again, just like we did before, we had talked about the dot product, right? We had it here in the predict, but this one works really well because the weights and the biases are already trained, right? In the predict function. Here, we still need to do the same operation. It's just that our weights and our biases are no good yet. Okay, so then I'm going to do NP dot for the dot product. That's going to be the dot product between xi, which is the current sample that I just grabbed, x1 and x2, times the weights, which is this vector, also of size 2. Remember, they both need to be the same dimension, right? So if you have x1, x2, that's 2. And if you have w1, w2, that's 2. So they need to be same dimensions. And so I did the dot product plus the bias. Plus the bias. Okay. So this is the idea here. We've done the dot product. Now I'm going to run this through the activation because this is still predicting values, any real valued number. We just want numbers between 0 and 1, right? Because it's predicting a 2-class problem. Does that idea make sense? The stepper, right? Any value, it currently predicts a value, could be negative, could be positive, right? But we just want it to be 0 and 1. So we're going to call that activation function. We defined it down here. There it is, right? So if the value is greater than 0, it's a 1. If it's less than 0, it's a 0. All right, so I'm going to go over here and do that. So I'm going to, now it's called ypred, and ypred is going to be equal to activation function. Activation function. And we'll run through it linear output. Right, so we run through it linear output. And so this is our function. Yeah, go ahead, please.
Why don't we just use the predict function we already have?
It's a good question. So what's in the predict function? Yeah, you're right. No, you're right. I'm not saying that you're wrong. This is not supposed to be the most optimal code, but you're right. We could have done that. In fact, it should be, right? It's the same operation that, so it actually brings up a good point, right? Ypred predicts. That's architecture. You see that? That's pure architecture. Here, this eventually will become a really complex neural net. So you're actually right in the sense that you don't want to have two. You see what I'm saying? Because you change one and you forgot to change the other. So you're right. So you could use this one. I just, for whatever reason, did it this way. Got it? All right, good. But yeah, it's a good observation. All right, so if we go back to the whiteboard over here, where are we in this cycle? So in this cycle, I would say that we currently change the color. So currently we can get to here, right? We can give it inputs and get these values. They're just not good. So if you remember, now comes this part that I kind of left as a black box. We need to compare the predicted to the real. And based on that, we make a decision, the update rule. Do you see that? That's stochastic gradient descent, right? So remember, we do the feed forward and the back prompt, right? And in this example, let me create a new one. So in the point of view of the feed forward, that's what we just completed. You see that? Feed forward just means I can predict values. Then I need to do stochastic gradient descent and back propagation, which basically means, or I should say, now I need to do back propagation, which requires stochastic gradient descent. That's a better way of thinking about it. You see that, guys? And so that means I need to adjust the weight. So right now, that analogy of the giant and the mountains, we're not going to get into that yet because this doesn't require it. Linear regression does require it, but it's pretty intuitive. And because you've taken your stats course, you already should have a slight background on that. And then here, we'll go over that idea. Okay. But now I'm doing backprop. The idea being that I want to be able to calculate these weights, right? Do it correctly. So I need a way to compare the values, okay? So that's usually referred to as the loss function, all right? So I need to calculate the loss function. So there's actually two functions that are really important, right? The predicting function, the architecture, and then the loss function. So we're going to start thinking about two equations, especially when we look at linear regression. But for now, we need to have, let's say, so we need way to compare predicted, let's call it Y-pred, to the real labels. Okay, so we need a way to do that, right? And this is in the Perceptron, this is called the Perceptron update. All the other ones work the same way, just a little bit more complex, but it's basically the same mechanism, okay? Which is actually pretty simple if you think about it. It's amazing how it's not, this idea is not complicated. Some of the things that enable it are a little bit more complex to understand, but the general idea isn't. So then, given that we have Y-pred, the simplest thing to do is to compare it to the real value, right? So the real values are in here, right? In Y underscore. So Y underscore. Now Y-pred is only the way that we've done it out of X train, right? Which might be 120 by 2. We're just grabbing one sample at a time. A more efficient way would have been to have grabbed a whole batch of values, right? 20 at a time, especially when you have millions of records. But here it's only one. Now, why this one is a vector, right? It's a vector of 120 by 1, because this is only the predictions. But because we need to compare, we can't compare 120 samples to just one, right? So we need to index out whichever one. And this is where the index of enumerate comes in and is helpful. Do you guys see that? So notice X train, right? And this is Y train, right? So these are the values from Y train. Okay. All right. So now I'm going to do then, I need the index, not the whole thing. So I'm going to use the IDX. Is this clear? All right, great. And so what do? The easiest thing usually in everything is to just take the difference. That's whenever you want to compare two things, take the difference. All right, so I'm going to take the difference here between the two, put them in parentheses, and that's it. Now I know the difference because I will know if the value that I predicted is if they're the same, what's going to happen? The value is always 0, right? But if they're not the same, you get another value, which could be positive, negative, etc. Think about it. If it's let's go over here. Think about now what's happening in this example. So let's do over here. Let's switch to red. All right. Oops. So let's say that the values are that, right? This is Y real. And this is Y-pred. So if we predict, and this is the difference, right? So if we predict 1, this is 0, right? The difference. If we predict 0, this is 0, the difference. If this is 0 and we predict 1, this is negative, right? And I'm missing 1. Which one am I missing? 1 minus 0, right? So if 1 minus 1, if it's really 1, but I predict 0, then it's 1. Do you see that? This is very useful because now you know, given these differences, they're the same, or the direction that you need to go in, positive or negative. Do you see that? So it ultimately becomes like an if statement of 3 rules. Oops, this should be plus. Take the weights and add to them something multiplied by this. If you multiply it by 0, what does that mean? You don't change the weights, which makes sense because the values, it's this scenario, right? It predicted exactly like the labels. So nothing needed for the weights. That's 0. If it predicts the other ones, then it decides whether you should add or decrease the weights. Do you guys get this concept? Guys, everyone? Everyone? Sure. This is like really important. Okay, I want you to understand this because it'll become more complex as we go forward, because I may add more like complex equations, but this is what's happening. That's why we start at the perceptron. That's the value of the perceptron, where we can see this little thing going on. Got it? And this is called the update rule. So now if we go to the code, we have this, and then we just complete it. We're going to call this the update, and we just decide what what that value is going to be. So remember that value that I told you about, learning rate, that 0.01, this 0.01. Now 0.01 multiplied times 0 if no change, multiplied times plus 1 makes it a positive increment, multiplied times minus 1 makes it you decrease by 0.01. And that's the trick. So then I'm going to plug in here the variable learning rate. You see that there. Oops, very nicely. And now this is the value that we need to, now this is just a little value, right? 0.01 positive, negative, or times, plus, minus, or 0. Now this needs to be used on the weights themselves. Okay. Now when we do deep learning, believe it or not, we have to do this for every weight. And this is where you can't do this, from scratch. And that's why we think we need things like PyTorch or TensorFlow, because they're literally made to do that. I mean, that was the big problem that needed solving. Okay, and through GPUs and that, it's done. And this is called calculating the gradients. So you'll see that a lot, calculating the gradients. The functions that we're going to look at in deep learning are a little bit more complex than this. Okay, and so there we have to look at the function itself, right? The curve of the function to determine if it should be a plus or a minus. Okay, and then I'll show you guys how that works. And that's why it's called gradients. And that's where it touches on calculus, because calculus allows you, when you take the derivative of a function on a point, it calculates something called the tangent. And the tangent is like the straight line that touches the function, right? So what's important about that is, I'm saying this now because there's a relation, so I want to link these things up so that when I talk about this later. But let's say that, just for the sake of argument, that your function looks like this, whatever, right? So you want to know if you should increase the weights or decrease the weights. Well, your value, the weights, is here, right? And it could be anything here, but that the function is here. So if you count, this is actually a bad example here. The derivative of of that function at that point is a straight line. You see that this has a shape, right? An angle, if you will. But what if the point is over here? Then that's the tangent. You see it's got a different shape. And what about this one, which that has a different shape? You see that? So what this tells you is, if you're here and it's like that, what does that mean? You should go in that direction, which means you should decrease the value of the weights. You see that? Because you move the weight in that direction. Remember, the weights are this angle, this axis here. If you're here and you get this tangent, what does that mean? The weight should go in that direction, so that means you go in that direction on this axis. And if you're here and it's like this, it's parallel to this. So my question would be, if you go that way, you actually go up. And if you go that way, you actually go up. So actually there's nowhere to go. Do you see? You have gotten to the bottom, and that means you've found the optimal point, because at the end of the day, this axis will represent the cost, and you're trying to minimize that. So anyway, this will become a little bit more obvious later, right? But I wanted to make this connection right now, that this thing, to calculate this, we need, it's called the gradients, right? And this is where we need a more advanced techniques like the derivative of a function. In the perceptron, we're doing something even simpler than that. And we don't need to do that. We just kind of in a rough way do this. Okay. All right. So now that we have that set up there, we've got the update. All that's left is that we actually have to update our parameters, right? So let's start with the simpler one. The bias is just going to be bias plus update. You see that? That's basically it. The weights will be similar. Just remember that the weights are a vector, not a value. So currently in update, we have one single value, but we need to update the vector of weights, which has W1 and W2. So then we're going to say weights is going to be equal to the weights plus update. Now we could multiply the update times the weights, right? But actually the practice is it works better to multiply it times the original x's. All right, so x I like that. So what is this equivalent to? This would be equivalent to, we have a vector of 0 and 0, right? So that's going to be in the first run. We have that, but then plus, now the x's do have values in them. Let's say it's got like a 2.3 and a 4.5, right? Let's say that's there. And then we just multiply that times the update, whatever it is. And so update plus or minus is going to be multiplied times this. So now 2.3 and 4.5 are going to be added to this and give you a new result. You guys understand? So after this one will be 2.3 and 4.5 for the first iteration. But the next iteration, this will be 2.3 and 4.5 times the update. And so they'll be updated. Is this clear? What's going on here? Would you like me to work out by hands one of these, or does this make sense? It wouldn't hurt, right? So yeah, so this equation, right? So let's look it over. So what's happening in there is, in the first, let's go by iterations, right? We're going by iterations here. In the first iteration, the values are 0, 0, 0, update, times whatever the values are, 2.3, 1.6, assuming these are the values of x, right? So this is x, so 2.3, 1.6, 1.7, 5, 0.1, 2, whatever the values are, right? And so we took that, let's say that this came out to 0.01. So that would be that would be 0.01 times 2.3 is 0.23. So this, I'm just going to write like the final one. So this would be 0.023. And then the other one would be 1.6 times 0.01, 0.016. You see that? That would be the result in the first iteration. In the second iteration, I'll use a different color here. In the second iteration, now you want to calculate the updated weights. The weights are now 0.023, 0.016. Do you guys see that? That's where they are. So now we predict again. We calculate the update. And now this is going to be for 1.75, right? So I'm bringing this over from this one. Times points, I'm just doing 0.01, but just keep in mind these would change. So now I do this, so this is going to be 0.023, 0.016 plus 1.7 times 0.01. That's going to be 0.017. 5 times 0.01, 0.05. And now we add it. And so this should be 0.023 plus 0.017. That's 0.04. And then the other one is 0.016 plus 0.05. And that's 0.066. You see, this is the process. And then for the next iteration, I won't do this one, but just kind of state it. Iteration 3, the weights are now 0.04 and 0.066, right? And now we repeat the process again. We update. Just keep in mind the update, this is changing, right? This is changing based on, so this is always changing based on this. So we're not just like randomly or in a foolish way changing that update. We have to use a smart technique, okay? If we just randomly did this, then, you know, we would need a quantum computer, as I said, to just like in parallel do everything, right? We don't have that. So we need to be pretty smart. And this is where a lot of the work comes in sometimes of how you do this, right? But for now, all we did is we took the predicted value minus the real value, as I explained, multiplied that times the learning rate. And that really just meant, if you remember, that really just meant, at least for the perceptron, that we ended up with these either -1, 0, or +1. So in my scenario, I always use 0.01. That means technically we always got +1, right? But if I could have used -0.01 when we would have gotten -1 or 0, in which case the weights just stay the same. Is this clear? Questions? This is an extremely important part of deep learning. In PyTorch, for instance, you actually say, you predict the value, you kind of then do this, which is called the loss, and then you literally say, I think it says backprop or something. You literally say backprop and go backwards. Okay, but the backwards part for us in this scenario is now this. This is the backprop because both lines here. Because if you think, we are going back to the weights and the bias and updating. You see that? We went forward, predicted, compared, now go backwards, update them. And that's backprop. All right, now we are not using stochastic gradient descent really here, but for more complex problems, like the one I explained of the functions, we have to, because this wouldn't be enough. All right, and that, believe it or not, we're done. Like, that's it. So the weights and the updates are modified. And so now we can the function can now go ahead and return the values. You see that? So the values can be returned. So I expect we'll have a few errors, I guess, but it should be ready to run. So let's run it. Yeah, so there's some error here. Where? Ah, yeah. Okay. Thank you. All right, try it again. Okay. All right. So it ran, right? Because this is Y test, this is Y pred. So by looking, so this is the real data. This is the predicted data. So what would you say about this model? Just by looking at the results. It's perfect, right? It does really well. That's right. Let's try a few more. Try 60. Is that 60? There may not be 60. That's the thing. All right, so now homework assignment. So this example, it's very easy, very straightforward. In this example, we have a classification problem, right, of 2 samples. So let's think about it. You just have to make a few tweaks to this. It has to be a binary problem to not have to change it too much. So do the following. Let's go to the web. So it's not a difficult homework, I think, but it'll be some coding there. No, it's this is too close. Here, let's go to the course website. I believe I have a data set. Yeah, MNIST is here, right? MNIST test or MNIST trade. So you have the CSV values in there. It's opening. So the labels are here, and then these are the values, right? So run the perceptron on MNIST. Because you need it to be a binary problem, what I suggest is, how many classes does MNIST have? 10. For every hand digit number, right? 0, 1, 2, 3. Just pick two numbers. Two that are very different, right? So what are two digits that are very different? Yeah. Well, digits. So it can only be the 10 digits. 0, 1, 2, 3, 4. 5 and 2 are different? That's your opinion? Okay. Are they the most different? That's what I. Huh? 10 is two digits. 0 and 1, right? Yeah, something, right? So pick two numbers, whatever you want it to be, because it needs to be a binary. You understand that, right? Instead, yeah, one or the other. So instead of using all 10 classes, just pick two classes. Use this data set. So you're going to discard the other 8 classes, right? Just don't use them. And then just build a classifier to distinguish between any two numbers as a CSV, then load it into the Perceptron code that we did today. Where is it? Oh, I need to. So you're going to load it into this code. So instead of using random data, you're going to load it. You guys have done that before, right? So basically what I want you to do is just run another data set through the Perceptron and see how well it performs, for instance, on the MNIST data set. Keep in mind, the dimensionality of this was 2. Now you have a dimensionality of how much? How many features for MNIST? 28 times 28, which is 784. It's not a difficult problem, but at the same time, you do have to tweak the code a little bit here and there. But most of it was written to work for any dimension. And that's kind of like the lesson here is that you should write code that way, right? That scales to other problems. Is this clear enough? What you have to do? That's right. So exactly right. So perfect. So whenever you want to use this line, right? You want to just reuse it as much as possible. But this line you cannot, because this was random data. So here you need to read MNIST and you need to read it in that format. Solve it. It's not difficult. All right, so let me create the assignment for that, but that'll give you something to play with for a while. So let's open up Brightspace here. All right. So I'm going to share this screen here. All right, so you're going to go in, I'm going to create this in content. I should have somewhere in here. So we're done with that. And we are here, Perceptron. We are actually done with the Perceptron. That's it. All right, so the next topic is linear regression, as I said, with code and everything. But here I'm going to add, here's the code, the link to the code. And I'm going to add a new assignment. Perceptron homework, and I'm going to say MNIST, just to kind of remind you of the data set. This will be due 7th, no, sorry, this class meets on 6th, right? So the 6th by 10 p.m. Open now. Stay open until Saturday. All right, so train and test the provided Perceptron code. So you're trying to see if the Perceptron code will work on MNIST, right? You want to see if something that was built in the 1940s, one of the original algorithms, at least for binary, will actually provide good enough results. You can actually compare. You can, and I'm going to say that in the homework. Benchmark this to Weka, for instance. That should be easy, right? So when you create your file, be very smart, right? When you create the file that you read into your code, make it in such a way that it's still a CSV that you can feed into Weka easily. You guys see that? So I'm going to say here, benchmark with Weka. Weka. Benchmark with Weka and see if Perceptron is as good as more modern algorithms. Okay, so you're going to benchmark with Weka and see if the Perceptron is as good as more modern algorithms. So train and test the provided Perceptron code. Remember, train and test the provided Perceptron code with MNIST. Let's say with MNIST data set. Make things simple. Select just 2 classes from MNIST. All right, so that it's binary. Okay. What else do I need to say? Benchmark with Weka and see if Perceptron is as good as. Yeah, that should be enough. This is clear enough, right? For what you need to do. You can also use just a test set, or you can use the train set. It's up to you. Or remember, train set has, I think, 60,000 samples. The test set has 10,000 samples. As long as you're consistent, right? So the point is, with Weka, use like naive Bayes, but also try multi-layer Perceptron or any of the other ones. Although that one's slow, right? But I think decision trees were fast or any of those. Try it out. Any algorithm really. Any algorithm really should be good enough for a comparison with the Perceptron, given the Perceptron was one of the first for this. Is this homework assignment clear? Do you guys understand? Right? And you know where the data set is. It's in the course website, so you can just get it from there. Questions about the homework before I save it? No? All right, so I'm going to go ahead and save this. All right, so this assignment has been created, and you can start working on it. All right, so we're done with the Perceptron. So now we can move on to linear regression. Okay, so we're going to do linear regression code on Wednesday. Okay, not today, but today I'll just start a little, light description of some of the theory behind linear regression. So I'm going to close this module, and you can see this is the next one, linear regression. Then after linear regression comes logistic regression. As you might imagine, it's an extension of this. And then multi-layer perceptron. And then if you notice, right after that comes Keras and deep learning, right? And it's all a sequence. And that really wraps up the semester for us. Keep in mind, exam 2 will be on April 11th, I think it is. Okay, so let's take a look at linear regression here. So I'm not going to do any more of the code. I guess I should say before that, were there any questions on the perceptron, or was it clear? Pretty clear, crystal clear. All right, so in the linear regression, so this is an idea from your stats classes, right? So you took linear regression. So let's actually start here. What can you guys tell me about linear regression? Let's start with you guys. How many of you have taken that stats class? Raise your hand. Taken it? Have you taken it? All right, great. So you took the stats class. What did you learn there about linear regression? Mm-hmm. What's the point of creating that line?
See how far similar data is to it.
Okay. Anyone else? What else can you say about linear regression? What's the point of it? Can you use it for something? Yeah. To predict. What do you predict?
Any sort of problems, like there's predictions, like what's the chance of, some of the questions, like what's the chance you reach the bag of marbles and it'll be green or red based on the marbles there are, and do the calculation, it's like 0.77 is blue.
But that's more like a probabilistic problem. That sounds like probability. But that's not linear regression. Yeah, go ahead. And how would you use that? Like, give me a scenario where you could use linear regression.
So you have, I don't know, specific one, but just something abstract, you have a bunch of data, say, from like previous time periods, and then you want to predict what, maybe like weather or something, what happens in the future, so you choose, X equals 10 or whatever, and then it would spit out a Y value.
Perfect. Exactly. Very good. And what you just said, doesn't that sound a lot like, like you just described, you said your words, I'm going to pick some X and then I'm going to get some Y, right? Well, doesn't that sound like same thing, right? And it's actually that's exactly right. That's what we're doing, right? So linear regression is, now we just used this equation, right? Seconds ago. Exactly. So you can see how the connection's right there. The goals are a little bit different. Before, so in supervised learning, we're usually trying to say, is it a cat? Is it a dog? So we're predicting classes. In the previous example of the perceptron, what were the classes? 0 and 1, right? In MNIST, we have 0, 1, 2, ... 9. In iris, setosa, virginica, versicolor, or 0, 1, 2, right? We're always predicting classes. In linear regression, we predict real valued numbers. From minus infinity to infinity, any value. But usually they're going to be governed by the type of data that we have. There's not going to be any problem really where the value would be this, right? You know, if I'm predicting the price of a house in Northwest Indiana, right? It's not going to be minus infinity or plus infinity, right? But it can be anything from 0 almost to millions of dollars, right? In a similar area. And so that's the difference between linear regression. So in linear regression, we are trying to predict real valued numbers. Now we had that mechanism already. If you think about it, we're kind of going, it's almost like we're going in reverse, because we had that mechanism. If I go to the code, where's the code? So if we go to the code, we did this here, 2 steps. The first step is exactly the formula of linear regression. Notice that predicts minus infinity to infinity. You just take the dot product of an x times a weight plus a bias, you predict a value. Do you guys see that? A real valued number. What made it a class problem where we limit it to zeros and ones was actually the next step, the activation function. You see that? Because this is where we said, if you look at the activation function, what do we say? If the values are negative, it's 0. If the values are positive, it's 1. So we just converted it to a 2-class problem. Make sense? You see it? Yeah, perfect. So if you think in classification, we're always doing this 2-step process, but step 1 is a linear regression. Now, the way we updated the weights also changes. So here we did this to update the weights. In linear regression, we're going to do something slightly different. You see that? And it's only because we have one specific objective in linear regression, which is the best fit line, as you said. Whereas in classification, we will have other objectives. And I'll give you an intuitive scenario of what I mean by that. If we go to the whiteboard, you said, let's imagine that we have, it's actually going to be data, right? So let me see how I can do this. Actually, I can do it like this. And I'm going to try to, this is meant to be the same data set. Do you guys see that? So it's meant to be the same data set, right? In linear regression, I have an objective. But in supervised ML, right? For classification, I have a different objective. But I'm creating the exact same thing, a line. So in both cases, so let me use a different color. In both cases, I want to create, so I'm going to use like a straight line like this. In both cases, I have a machine, the machinery to create that line. However, the angle of that line is different based on the objective. Why? For classification, which line do I want? I want to separate the zeros from the x's, right? So probably, oops, what's going on? Hold on. So probably, imagine that's a straight line. That's the line that I want. Okay? That's the line, a straight line. That would be a straight line. There we go, straight line. All right, that's the one I want. But in linear regression, what is it that you said? Best fit line to this data, right? So we're not going to treat it as different things. We want that. Do you see that? We fit a line because, as you said, I want to be able to predict with just one line a future value. Given an X, you know, what's it going to be? Yeah, go ahead. Here, that's not the objective. The objective of it is not to look at two things. Any point on this chart is treated equally. You see that? Because that's its objective is not to differentiate. It's only to create a straight line. That's linear regression. Whereas with supervised machine learning classification, where we do have zeros and X's, its objective is to differentiate between two groups. And then it still creates a line just like this one, but a line that best separates the zeros from the X's. So what I'm trying to say is, you know, the function for creating a line is the same. You know, a lot of things are the same. The objectives are going to be a little bit different. The way that we measure performance is different. How do we measure performance? So let's, in this scenario, if we get an X here, that's a bad, oh, I'm still using that. In this scenario, we get that, that's a bad thing. We get that, that's a bad thing. We get that, that's a good thing, even though it's really far from the data. It's on the other side of the line. In linear regression, that's a good thing. That's a good thing. That's a good thing. But if I get an X here and a 0 over here, even though they might be on opposite, on the right side of the line, it's too far from this group. So that's the objective. You see that? Questions? No questions? So I haven't really gotten into how we train. I'll do that on Wednesday or later. But for now, that's kind of what I want you to understand, is that there's a lot of similarities because it's the same vector space, same data. We still fit a line. It's just the line is fitted differently. And really all that changes is the angle. Here we are trying to separate between two groups. Here we actually try to fit a line to the whole group. Okay, that straight line. We'll see this. Now the question is how we're going to fit also, right? So that's going to be another issue for us to explore. Because, you know, if we just focus on the linear regression now, how do we measure? Oh, and I'm going to stop using X's. I'm just going to say points. Let's say there's a few points here too. Which one's the best fit line of the two? The brown one or the blue one? Why? More points are in that general area. The way that you measure it is performance here. This is the real value, right? Which represents the value here, right? X. The predicted is right there. Would you agree? So like if I gave it this X, right? The corresponding Y would give you that. But if I give this X to the function of this line, which by the way is, right? If I give it, it predicts this one. You see that? So what do? I take the difference between the two. That's the delta distance, let's say. You see that? Now this other line over here, do the same. if this is the real value, right? This is the real value. What is the predicted given this line? Here. Do you understand that? What's the difference between the real and the predicted for this line? Do you see that? That's the delta. Let's call this one line 2, and then this is line 1. So then we can say 2 and 1. Which one of these? So what would you say about if I compare delta D1 versus delta D2? Which one is bigger? D2. D2 is in fact much bigger, right? So that's how you select the line. The line is going to be the one that what? How would you generalize this concept? Go ahead, sir. Nope. Based on what I said here.
The shortest distance between the predicted value.
Yes, but that's just for one point. But it's for all these points. So which is the best line? It's the best line. The best line is the one where the sum of all the differences between the real and the predicted is minimized. You see that? And that's the sum of squared errors. Least squares, right? Which is a function I'm pretty sure you covered in that class. I think there's a, oops, no, that's an n. And this should be from I equal 1 to n, where n is the number of points. So you see what this means? This means that if this y hat is this point, then this y is the real point. So that's the difference. Why do we square it? To get rid of the symbol, right? Because some values will be on the other side of the line. They'll be negative or positive. That would cancel each other out. By squaring it, we get rid of the negative, and we just know distance. Does that make sense? And so now we do this for 1, but then I have another point, x2. So the real one, let's say, is that one. This is what this line predicts. So that's this other delta. But the brown line here predicts this. So that's even bigger, you see? So again, for this point, the best one is this, not this one, because it's too big. And so now we can calculate an infinite number of lines, right, in this chart. You pick the one where this expression here is the minimum, is minimized. The sum of the, that's why it's called the sum of the squared errors. They're square, the error is this, y predicted versus y real, squared to get rid of the negative, and it's the sum for all the points in that idea. Got it? All right, take that idea with you, think about it a little bit. Should be like a very nice one. And then we'll pick up here next class, and then also start working through the linear regression code. Any questions? But this is pretty important as we start to move on to deep neural nets. Keep in mind, it's all the same thing. All right, that's it. So I'm going to stop the recording here.